Alright, welcome to the final solution video, and this one is for the bonus problem of the competition, which was last robotics. So this was, I would say, the hardest problem by far to find the solution to. It was recursively based and kind of based in binary numbers, which you'll see why later. But here's the problem. If you want to pause and read through it, that would be great. It's based off of First Robotics, which is kind of the pun with the name. And hopefully you enjoy the flavor text. So basically what the problem has is it gives you a string. The string starts off as R. And then you double the string and then flip each letter from R to B and from B back to R. So once you do that, you get a string that kind of resembles this. And the important thing to notice about this string is why each letter is what it is. So you've got R, and then you have R, and you change that to B. You make that letter B, and you change this to, you change RB to BR. Concatenate that on. Then you keep going, R, B, B, R. You flip that to B, R, R, B. And then you can go on indefinitely. So the first thing to notice is that if we label our indices, starting at 0, of course, one thing you might notice if you wrote it out long enough is that the powers of 2 all happen to be B's. And that's actually true indefinitely. That's provable. And in fact, we'll prove it right now. So the question is, why are they B's? Why is every power of 2 B? So 1 is B, 2 is B, 4 is B, 8 is B, 16 would be B. And why aren't any of them R? Well, when we have a string, the string starts off at length 1, and then it doubles, and then it's length 2 after we concatenate the opposite to the end of it. And then after it doubles, it's length 4. And then after it doubles, it's length 8. So a certain index, if an index is the power of 2, right? So for 1, what that is that's the beginning of what used to be string 0. Index 2 is the beginning of what used to be the string from 0 to 1. Index 4 is what used to be the beginning of the string from 0 to 3. Index 8 is the beginning of what used to be 0 to 7. And then it flips, obviously. So any power of 2 is the first part of the flipped string. And the other thing we should notice is that, there's my eraser here. The other thing we should notice is that when you increase the length, or when you keep going through this pattern, you can change you can increase the length, but the beginning of the string never changes. So the parts you've already established don't change because you're just concatenating more into the end of them, right? So you know that index 0 will always be R, index 1 will always be B, no matter how many times we do this. So we don't have to worry about that changing, and because of that, because index 0 is never going to change, and every power of 2 starts with the opposite of what used to be 0, every power of 2 is going to be B. In general, the thing to notice is that you've got a string that's just 0, and the string from 0 to 1, and then a string from 0 to 3, and then a string from 0 to 7, and it doubles in length each time. But if you let's look at index 7, right? Index 7, where did it come from? Well, you had a string 0, 1, 2, 3, and then you copied the reverse of it this way. So index 7 is the opposite of index 3. Because this was the first string, and then you copied it, and you flipped everything, and then it came to here. So index 7 is the opposite of index 3. Where did index 3 come from? Well, index 3 is part of this string, which is the opposite of the string from 0 to 1. So 3 maps onto 1, and it's the opposite of 1. And 1 came from the string 0, so 1 maps onto the opposite of 0, and then you're done. And you can continue that indefinitely. That works for every index, and in fact, that's actually a solution that's fast enough to solve in time. Because if we look at the problem, the input can be absolutely enormous, 10 to the 18th. So we can't do that in n efficiency. We can't do that in square root of n efficiency. We have to do that in log n efficiency, which is, or log n or something near that. We can't do n log n because that'll be way too slow. But we have to do something around log n efficiency. And this actually turns out to be what we just drew. Turns out to be log n efficiency because each time you're subtracting worst case the next power of 2. So the first instance you could pick 4, you can only subtract 1. But after that you're subtracting the biggest power of 2 less than that number. So you can figure that out. You can find the biggest power of 2 less than a certain number. That's pretty easy to do. You can find that out in log n efficiency, the biggest power of 2 less than a number. You can just check powers of 2 up to that, multiply by 2 each time, and then once you get to a number that's bigger than it, it's the last power, the power of 2 before that. So that would work. But the thing is, you don't actually have to do that because, well, that would work, and that would be log of n all squared, which is different than log of n squared. So that would be fast enough because log of 10 to the 18th is like 60 or something. I don't know, something relatively small. And you can definitely process that. 60 squared is something under 10 to the 5th, right? Definitely. So you would be fine. You can do it as much as you want. But there's actually a faster way. Oops, there's a faster way to do that. So what you'll notice is we were subtracting the biggest power of 2 less than a certain number, and then flipping each time we did that. So what we really want to do is we want to see how many times can we subtract the biggest power of 2 less than a certain number. And one thing you might notice if you're familiar with certain ways of counting and with different number bases is that's actually how you determine what a number's binary representation is. So for the number 13, for example, that's kind of a cool one. We've got, well, let's write out the powers of 2 first. We've got 0, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2, sorry, is 4, 2 to the 3 is 8, and we'll stop at 2 to the 4, which is 16. Okay. So the way we figure out what, and then you could keep going forever, but we won't need to. You'll see why. So to figure out what the binary representation of 13 is, you compare it to the biggest binary number you can. So in this case, 16 is the first one bigger than it. It's smaller than that, so we put a 0. And in the event that's bigger than it, in which case 8 is, or 13 is bigger than 8, so if 8 is smaller than 13, we'd put a 1, and then we would subtract 8 from 13. So if we did that, we get 5. And we've put a 1 here to indicate that there's 1/8 that goes into it. And there will always either be 0 or 1 of the power of 2 if you do it this way, because you're multiplying by 2 each time, right? So you would never reach 2. So for 4, 4 is also smaller than 5, so we'll put a 1 here. And then we've got a 4, or we subtract 4 from it, and we get 1. 2 is bigger than 1, so we put a 0, because we can't subtract 2 from 1. And then 1 is equal to 1, so we subtract 1, and we get 0. So this is the binary representation of 13, 1, 1, 0, 1. And what that's saying is we would have flipped over 8. So we'd have 8 things here, this would be 8, and then we would have another 8, and 13 would be in this section somewhere, right? So we flipped the number, when we copied all of these, we flipped all of them, and in doing so, that's what this 1 represents. It represents that we did flip on when the length was 8, we flipped to get to 13. Then the 4 represents when we were in the 8, right? this had a length of 4. We did flip to get to 13 because 13 is over here somewhere. So we had 4 and then we flipped to get to 13. So we flipped over both 8 and 4. So both of those are 1s. And then for 2, what the 2 is saying is that 4 was in 2 pieces, but we weren't in the second half for the 2. We were in the first half for the part that matched onto 13. So since we didn't flip for 2, there's a 0 there. And then finally, we did flip over this. So when the length was originally 1, we flipped to get it to 2, which ended up being the thing that matched onto 13. Is that the case? I think so. All right. Should we draw it out just to make sure we had this all right? Let's do that. Red, blue, blue, red, blue, red, red, blue, blue, red, red, blue. Sorry, blue, red, red, blue, red, blue, blue, red. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, so we don't really care about this. So we had 0 to 7, right? We flipped at the spot 8, and we got 13. So this was 0, 1, 2, 3, 4, 5, spot 5, which was red. So we'll highlight that. All right, and then where did 5 come from? So we had this half right here, and then that doubled. So 5 came from spot 1. All right, so we were right. And spot 1 came from just the 0. So the 0 flipped to 1. Then the this half flipped over here, and then this half flipped. Sorry, this part right here flipped to over here. So that's we got our binary right, and you'll notice that both of these are really the same algorithm. So you can do it either way. The second way is iterative instead of recursive, so that might be a bit easier. Both will work, of course, if I haven't made that clear. So the first number we're given, well, we're going to need a scanner first. First number we're given is the number of test cases. And then after that, we're given these your rank. Okay, so that's 1. And we have to, since this is 1 indexed, we have to subtract 1 from that. So that's going to be a long rank equals s dot next long minus 1. And then what we want to do is we want to count the number of 1s in the binary representation of your long. So string as string equals long dot to binary string. Awesome. Break. This will give us the binary string. Now we want to count the number of 1s. So we're going to go through each index of the string, and at each index, if as string dot caret, oops, if the caret I is equal to 1, then we know that we flipped. Okay. So if we flip an even number of times, that means we would have red, because if we started a red and we flipped 0 times, we'd be at red. start at red, we flip twice, we go from red to blue, and then blue to red again, so we'd stay at red. And flip an odd number of times, we'd be at blue for the same reason. So if counter mod 2 is 0, then we have one thing, otherwise it's something else. This was red, I think. I forgot exactly what the syntax is here, what they wanted. Okay, yeah, red or blue. Awesome. So that is the implementation. Let's see if what we did was significantly wrong. We failed the example test cases. So all right, so we're right. That's how you do it. So that is that's the bonus problem for the competition. Last Robotics Black Balloon. No one managed to get to this problem because no one was able to figure out the graph theory problem. But it was there just in case teams had the time to get to it. And if you weren't able to solve this by yourself, don't feel bad. It was, of course, it was intended to be something that was a challenge for 4 people in an hour with 2 computers. So this was the or 4 people in 3 hours with 2 computers. So this was for the teams that were really up there, just to make sure no one was sitting there twiddling their thumbs, like has been the case at Marquette in certain years. So we didn't want that. So this was the hard one. If you have any comments on any of the problems, if you liked them, if you would improve, or if you would improve on something, if you liked the flavor text, if you didn't like the flavor text, if you would have preferred just a simple dry problem statement that you can get right into, feel free to let me know. You can also email me at the email in your packet, as I mentioned in the introduction to the series, and be sure to come back next year. So thank you for watching, and goodbye.